This video is on exponent rules as they apply to division. First property we're going to take a look at is called the quotient of powers. So to divide two powers that have the same base, we want to subtract their exponents. So the rule says a to the m divided by a to the n equals a raised to the power of m minus n. So for example, x to the sixth divided by x squared is equal to x to the 6 minus 2, or x to the fourth. So why is this true? Well, if we have x to the sixth power divided by x squared, we have x times x times x times x times x times x, 6 x's, divided by 2 x's. And what happens is these x's cancel out, and we're left with x times x times x times x, or x to the fourth. Let's take a look at an example here. Here I have a to the fifth, b to the fourth, divided by a, b squared. If you want, you could actually write this as two separate. So a to the fifth divided by a, and times b to the fourth divided by b squared. Let's subtract our exponents, so that's going to be a to the 5 minus 1 times b to the 4 minus 2, or a to the fourth b squared. Next rule is the power of a quotient. To find the power of a quotient, find the power of the numerator and the power of the denominator. The rule is the quotient a divided by b raised to the power of m is equal to a raised to the power of m divided by b raised to the power of m. So for example, if I have 2 fifths to the third power, that's the same as 2 to the third power over 5 to the third power, or 8 over 125. Why is this true? Because 2 fifths to the third power is 2 fifths times 2 fifths times 2 fifths, which across the top is 2 times 2 times 2, which is 2 to the third, and across the bottom in the denominator, 5 times 5 times 5, which is 5 to the third. Let's take a look at an example. So here I have 2x squared y divided by 3, the whole thing cubed. So this is going to be the same as 2 thirds cubed times x squared cubed times y cubed. So 2 thirds cubed is going to be 2 to the third power, which is 8, over 3 to the third power, which is 27, times x to the sixth. Remember, multiply the exponents, power of a power, y to the third. And if we want to go ahead and put this back into one expression, the 8 is in the numerator with the x to the sixth in the y cubed, and the 27 is in the denominator. Our next rule is the zero exponent property, and it says that any non-zero base raised to the power of 0 equals 1. So the rule is a to the 0 power, or anything to the 0 power, equals 1. So for example, 7 to the 0 equals 1. So why is this true? Actually, you can look at it two different ways. If we were to use the division property, the quotient property, we would have x to the fifth divided by x to the fifth, which is x to the 5 minus 5, or x to the 0. And we also know that x to the fifth divided by x to the fifth equals 1. Any number or any term divided by itself equals 1, so therefore we know that x to the 0 power equals 1. So here's an example. Simplify 3a squared b to the fourth divided by 6ab, the whole thing raised to the 0 power. It doesn't matter what's inside the parentheses here. If this whole quotient is being raised to the 0 power, that is just equal to 1. Next property is the negative exponent property. And it says a base raised to a negative power is equal to the reciprocal of the base raised to a positive power. Here's the rule. It says a to the negative n power is equal to 1 over a to the n. Notice that this is the reciprocal of a to the n, and a to the n ends up in the denominator. And 1 over a to the negative n is equal to a to the n. So for example, x to the negative fifth is equal to 1 over x to the positive fifth, and 1 over x to the negative fourth is equal to x to the fourth. So why is this true? Well, if we did our quotient property here and we had x squared divided by x to the fifth, that would be x to the 2 minus 5, or x to the negative third. But if we also looked at that in terms of x squared being x times x to the fifth being x times x times x times x times x, and we did our canceling here, that leaves me with a 1 on top, and I have 1 over x to the third. So x to the negative third power is equal to 1 over x to the positive third power. So let's take a look at an example here. And these can get kind of tricky. So we have 5 r to the third t to the fourth divided by negative 20 r squared t to the seventh u to the negative fifth. I'm going to break this up actually into 4 fractions. Let's deal with our coefficients. So 5 over negative 20 times, now I'm going to look at my r's. R to the negative third over r squared, and then I have my t's, t to the fourth over t to the seventh, and I don't have any u's on top, so I'm going to put a 1 on top there over u to the negative fifth. And let's simplify each one of those. 5 over negative 20 is the same as negative 1/4. R to the third divided by r squared is going to be r to the negative 3 minus 2, remember the quotient property, times t to the 4 minus 7 times, well, this doesn't have anything on top. That's just going to be, I'm going to leave it that way. Oh, I'm sorry, I made a mistake here. That should be u to the negative fifth. Okay, so I am going to change that so I can make that a u to the positive fifth power. Okay, so that's going to give us negative 1/4 times r to the negative fifth times t to the negative third times u to the fifth. Now let's go ahead and clean that up. What's going to be in the numerator? Well, actually, why don't we start with the denominator? I'll have 4 in the denominator. This r to the fifth r to the negative fifth becomes r to the positive fifth in the denominator, t to the positive third in the denominator, and then I had a u to the fifth on top. I don't need to put my 1 there, but I do need to remember to have my negative, and I'll put that out front. So how do you know when you've completely finished simplifying an expression? An expression is completely simplified if each base appears only once. So your problem has only one a in it, one b in it, one x in it. There are no powers of powers. Basically, you've gotten rid of parentheses. All of your fractions are simplified, as we did in the problem above. We had 5 over negative 20 and reduced that to negative 1/4. And there are no negative exponents. So here are a couple practice problems I'd like you to try. I have 4 of them here. So stop the video and give these a try for yourself. Okay, let's take a look at these problems. So I have k to the 7th, m to the 10th, p, divided by k to the 5th, m to the 3rd, p. So I'm going to subtract my exponents. So I'm going to have k to the 7 minus 5, which is 2. Oops. M to the 10 minus 3, which is m to the 7th. And p to the 1 minus p to the 1 is just p to the 0, or 1. My p's cancel out. So I have k squared m to the 7th. Next example, 2y squared divided by 3z to the 3rd, the whole thing squared. So I'm going to square each term in the numerator, so that 2 squared is 4. Y squared squared is y to the 4th. And now the denominator, 3 squared is 9, and z to the 3rd power squared is z to the 6th. Okay. Number 3, I have negative 4n squared q to the 5th r squared divided by 9n to the 3rd q to the 2nd r. The whole thing raised to the 0 power. Don't let that throw you off. That's just equal to 1. And our last problem here, 32a to the negative 8th, b to the 3rd, c to the negative 4th, divided by negative 4a to the 3rd, b to the 5th, c to the negative 2. So I'm going to go ahead and write this as, I think it's going to end up being 4 fractions here. So 32 divided by 4, deal with your coefficients as though they're a normal fraction, times a to the negative 8th over a to the 3rd, times b to the 3rd over b to the 5th, times c to the negative 4th over c to the negative 2. Okay, 32 divided by negative 4 is going to give me a negative 8. This is going to be a to the negative 8 minus 3 times b to the 3 minus 5 times c to the negative 4 minus negative 2. And that's going to give me negative 8 times a to the negative 11th times b to the negative 2 times c to the negative 2, which is going to turn into, so it looks like all of my exponents are going to be on the denominator. I'll have a negative 8 over a to the positive 11 in the denominator, b to the positive 2 in the denominator, and c to the positive 2 in the denominator. So in this video, we took a look at exponent rules as they apply to division.